So let's look at some examples of how we can declare arrays in C and also try and take a look at the address locations that get assigned to them, right, so that we get a better understanding of what it means to actually talk about consecutive addresses. So this code that I am showing over here basically is a simple function that declares an integer array variable, and then what it says is that it actually takes a, right. This is not a of 0, it is not a of 1, it is not a of 10, it is just the name a and casts it as unsigned long. And the reason why this works is when I declare something as int a of some number out here, what is actually happening is it is creating a pointer. So a is of type pointer to integer, which is why I can cast it as unsigned long and print it out here, and it should show me an address. Now what I am doing further is, after that I then run a for loop which basically goes from 0 to 10 or 0 to 9 and says prints the address of a of I, right. So a of 0, a of 1, a of 2, it will print out all of those addresses. I am specifically printing them out in unsigned decimal format over here, right. In the previous case this was in hexadecimal just for convenience of how it is denoted in memory, but this whatever I print in hexadecimal and what I print as decimal over here are exactly the same numbers, right. It is just a different way of sort of looking at the values, right. So let us see what happens when I actually run this. It compiles and then it prints out this information saying that the starting location of a is some value, right, this 8C09 1EB0. The point is this changes every time you run. So if you run it again, for example, you get a different address out here, right. Remember that the address is not determined by the compiler, it is not determined by you, it is determined by the operating system when the program actually runs, and every time you run it you are going to get a different set of values out here, right. You may just by accident get the same value more than once, but in general that is unlikely to happen. Okay. Now this value out here is printed in hexadecimal, the same value is printed here in decimal because this address a of 0 is exactly the same as the value of a, and you can verify that the decimal value corresponding to this hexadecimal out here is actually this big number 1407 etc. that we see out here. Okay. Let me actually just clarify on that. It is not going to be exactly the same, and the reason for that is because what has been printed over here is actually just the first 32 bits of this. When I do a %x out here, it prints only the first 32 bits of the unsigned long, right. So I think it should actually be done as long x in order to get a better value, and now you can see that it actually prints out a much longer value, right. And the reason I said that is because anything which is only a 32 bit value can at most have a decimal value which is 2 into 10 power 9 or 4 into 10 power 9 if you treat it as an unsigned value, whereas these numbers over here are clearly longer than that. Okay. So what is actually happening out here is that this is one fairly big number, right. The 7FF basically indicates that it has been mapped somewhere fairly high up in the virtual memory of this computer that we have. Okay. But what is actually happening is something else. This number is just a completely artificial number that is created by the operating system and has no real relevance to physically where the data is stored, right. And the reason is because the operating system essentially creates a virtual view of memory that can be used by the system, right. And the only thing that you get to see as the end user is your virtual memory. You do not actually in general get to see where in physical memory your data is stored. The reason for that is partly to protect processes that are running inside the computer from each other. It should not be easy for one process to guess where in the memory some other process has stored its data, because then I can basically leak data, I can get data from some other process that I do not have access to, right. So these numbers are mostly irrelevant, they are not particularly useful by themselves. What is useful is the pattern that we see over here, right. Look at the last, well, 2 digits, or 3 digits essentially that we have here, right. You can see that there is a clear pattern. A of 0 ends with 776, A of 1 with 780. That clearly indicates that the address of A of 1 is exactly 4 bytes greater than the address of A of 0, and then to A of 2, A of 3 up to A of 9, right. So, I have a clear set out here where the addresses are increasing 4 bytes at a time. Okay. Now, what happens if I change this to short, right? Nothing else changed. I am just going to run the exact same program again, and now what you see is now the addresses are incrementing by 2, right. So, A of 0 is at one particular location, A of 1 is just 2 bytes more than that, A of 2 is 2 bytes more than A of 1, and so on, right. If I made it a char, then I would see that it is basically 1 byte. Now, I have 66, 67, 68 and so on, right. And that in some sense clearly shows you that the size of the char data type itself is only of size 1, which is why this is happening, right. I could also go further out here and look at, for example, what happens with float. And since we know that float is 32 bits, once again I see that the addresses increment by 4 bytes, right. What happens with double? It goes up by 8 bytes. I have 24, then 32, then 40 and so on, right. So, the increment from one location to another is 8 bytes. And finally, I could actually have a particular data type which is called long double, right. And if you run this, you will actually find that the increment over here is 16 bytes. So, a long double data type is actually 16 bytes or 128 bits wide. It is not commonly used. It is something that is used in certain kinds of computations that require very high precision, right, in certain kinds of scientific computation usually, and it is a data type that is available in the language. It is probably also not the most efficient data type to use because the hardware by itself does not support 128 bit floating point numbers, right. So, usually this will end up being much slower than if you had some other kind of simpler data type like float. Okay. So, the default, of course, I mean the thing is we used int, but even if I give unsigned int, it is going to show me exactly the same thing, right. It is going to show me 4 bytes as the delta between one address and the next. The difference between int and unsigned int is only in terms of how the MSB or the sign is actually handled. Okay, in this next demo function, what we are going to do is use the Sizeof operator, right. Remember that I had mentioned earlier that Sizeof is not actually a function, it is an operator, and part of the reason for saying that is it is actually something that runs at compile time, not at runtime. So, in other words, it is something which the compiler itself looks at and needs to be able to compute values and basically tell you what is happening, right. So, the Sizeof operator can be used in order to find out a lot of useful information about an array, right. So, in this case what I have done is also I am introducing another way of declaring the array, which is that I specify constant nmax is equal to 1000 and then use nmax over here, right. So, if I did not have the constant, let us see what would happen if I try running it. Well, it still runs, right, and the reason is because the compiler is actually able to understand in the context of this program that nmax is declared out here and then is used immediately after that for declaring the array, right. So, it uses the value that it sees for nmax just before defining it out here in order to see what the value is. But it is always safer to specify it as a const integer to make it clear to the compiler that this value is not going to change. Okay. So, I have const int nmax is equal to 1000 and I declare int a of nmax. I have also just declared this int sum over here as something which is performs some operation on the data that I have. Okay. And what I do is I am printing out a few pieces of information. One of them is the size of an int, right. Let me just comment something out here for now. I am going to ask it to print the size of an int. After that I am going to ask it to print the size of A, and then to print the number of elements in A, right. How do I get that? I take the size of A and I divide by the size of int, okay. And let us run it. What we see is the size of an int is 4. It returns its value in terms of number of bytes, not bits. And the size of the int array, that is A, is 4000, right. It has 1000 elements out here, and therefore we basically have an array of size 4000. The number of elements is the size of A divided by the size of int, which gives us 1000 as expected, okay. Now, one thing to keep in mind with regard to this declaration, what happens if I give nmax is equal to, let us say, 10 out here, right. The first thing you can notice is that even right here I have got a warning from my editor, right, which basically says cannot assign to variable nmax, which has been declared as a const variable. This with const qualified type const int and so on is just a complicated way of saying it has been declared as a constant, do not try to change it, right. What happens if I actually try to run it? As expected, right, exactly that same error which came in the editor out there is also going to come out here. But now what happens if I remove the constant, right, and then run it? Look at what happened. I have changed the value of nmax to 10, but the size of A remained 4000 and the number of elements in A remained as 1000. In other words, it took the value of nmax at the point where the variable was declared and used that to perform the computation, okay. Now, this works because nmax is declared and the compiler knows the value of nmax at this point in time when it is actually declaring the variable A, okay. So, what is required for the compiler to work is that it should be able to analyze the size of nmax that is required for the variable A to be declared at compile time. As long as nmax can be derived as a constant, it will be able to declare an appropriately sized variable, and then it can answer all of these questions. What is the size of A? What is the number of elements in A, which is obtained as size of A by size of the data type of A, right. What if I change this from int to, let us say, short? Then I would basically need to change this to short and to change this also to short, and that is basically it. When I run this, it would show me that the size of, well, I did not change the word over here, but it is 2. The size of the array is 2000 bytes and the number of elements is 1000 bytes or 1000 elements of size 2 bytes each. Okay. So, you can basically play around with this as you like. Right. Now, in addition to this, I have also got one small piece of code out here which tries to do something, which is it just adds up the values in A. Okay. So, I am saying for int I is equal to 0, I less than nmax I plus plus, sum is equal to sum plus A of I, sum has been initialized to 0. So, let us see what we are going to get over here at the output, right, when I actually print this value of sum out. Let us run through this, and what we find is that yes, in this case, the value of sum actually turns out to be 0. Let us see if we can change this. I am going to try changing it to 10, remove this nmax and run it one more time. You will notice that when I change the value of nmax to 10, nothing else went wrong, in the sense that the size of the integer array went up to 40,000 bytes, the number of elements in the array remained 10,000 as expected, but the sum is now showing a very strange number out here, right. And why is that? And the reason is because even though I declared A of nmax out here, I did not initialize it, right. And what that means is that C by default, in order to save time, does not explicitly initialize an array unless you have said you want it to be initialized. Okay. So, in this case I have not given any initialization parameters out here. What it ends up doing is it just declares an array, it sets apart memory locations for that. The memory locations exist. The problem is when I access those memory locations, they probably contain some junk that was already there from maybe a previous run of some program or the other. It might have been the data from some other program, or it might even be just random junk which came about because when I switch on the computer, a few of the bits flipped randomly to ones or zeros, right. Anything could have happened. The point is I cannot in general predict what those numbers were, right. So, this sum that you see over here is simply because this array was not initialized, right. What happens if instead I give a value like this? At this point I have explicitly asked for an initialization, but in this case it is actually complaining about it. It says that a variable sized object may not be initialized. What happens if we add a const int over here? Now that goes away. It does not have a problem with that because it is no longer a variable sized object. When I say something is constant, I know that nmax is always 10,000. I am never going to change the value of nmax over here, therefore I can do the initialization. Remember what we said about initialization? If I give only one parameter, it will automatically set everything else to 0. Okay. Does it work? What happens when I compile and run this particular program? You can see that the sum actually comes out to be 0, right. What if I initialize this to 10, right? What is expected to happen is that only a of 0 gets the value 10, everything else gets the value 0, right. And what happens when we compile and run this? We see that in fact as expected the sum is equal to 10. Okay. So, I could do something else. I could do 10 comma 20 comma and then say maybe the fifth element is equal to 100, right. And if I run this, everything else is expected to be 0. So, what I should see is only the sum of these three values 10, 20 and 100. And if I actually print the values out, I should find a of 0 is 10, a of 1 is 20, a of 5 is 100, everything else is 0 in this case. Okay. All right. So, let us remove the initialization. What the next thing that we might wonder about is there a limit on how big the array can grow? And the point is the programming language by itself does not really put a restriction on the size of the array, right. So, there is nothing in the language that enforces that you need to have a certain that you cannot have arrays of more than a certain size. So, you can see that when I changed it to 100,000 and removed the initialization, now again the sum became some random value. That is because I have now gone and hit some new locations in memory that were not initialized to 0, and they end up having something which adds up to this value out here. Why is it a negative number? I do not know. It just depends on what values were there. There was probably some overflow of the numbers, right. Beyond a point, the 2's complement means that when two large positive numbers are added, I end up with a negative number and so on. So, it could be any number of reasons why I have such behavior. But now let us look at what happens when I increase this number. So, I have continued increasing the size of the array that I am declaring to this point where essentially nmax is 10 million, right. Now, 10 million looks like a lot, but in the context of a computer is actually not a very big amount of memory, right. If you think about it, 10 million elements of size 4 bytes each is 40 megabytes. Most computers have memory in the range of a few gigabytes, right. But what has happened is over here, as soon as I declared this array out here and tried running it, right, it just exits with this status -1. It did not complain about the compilation went through. The problem came when I tried to run the program, right? And when I try to run the program, what happens is it actually loads the program into memory, it calls this function demo size, it allocates a stack for that function. Now a stack is primarily meant for local variables, and that is where our problem is coming, because stacks are typically have some kind of size constraints on them that are determined by the operating system and the actual runtime of the system that you are working with, right. They are not fixed, they depend on the operating system, they depend on a lot of other conditions, but they do have limits. So what that means is, even though the size of this array that we are looking at, 40 million bytes, is not by itself a very large number in the context of a computer, it is big enough that it does not fit in the stack frame of this function and the program crashes, right. So this exit status -1 is effectively an indication that it has crashed, something went wrong. It could not allocate the memory that was asked of it, and therefore it crashed and gave up. So now finally one more look at how we can do array initialization, right. Over here what you can see is that I have declared two arrays, right, int a, which has been explicitly initialized, all the values 1, 2, 3, 4 have been initialized out here, but int b has only two values initialized, and that too the values from starting from 2, location number 2. So it has basically 2 and 3 locations are going to have the values 7 and 8. And if I try to go ahead and print those values, what I find is, sure enough, a of a has been explicitly initialized, a of 0 has got the value 1, a of 1 has got the value 2, and then 3 and 4 as expected from this initialization vector that I have given. B on the other hand straight away says that b of 2 should have the value 7, and the next value after that, which is b of 3, should have the value 8, and by default it automatically initializes the other values that you have out here. Okay. So this is one way by which I can also do the initialization along with the declaration, right, and whatever has not been explicitly initialized will be set to the value 0.